Okay, so we just looked and we used a calculator to knock these guys out, and let's see where they come from and some of the problems that are solved by restricting some domains and ranges to get these things correct. Okay, so here is a graph of the sine of x. Okay, and we've seen this before. We graphed it and did all that good stuff with it, and is just the parent function of sine of x. Now, what we're going to do is that we have the sine of x and it equals y, just like that. Okay, so if we were to switch around the x and the y, okay, it would be something that looks like this. Now, this over here is the sine of x equals y, okay, that guy. This, in our first step of creating an inverse, would be the sine of y equals x. So the way that we build an inverse function is the same way if we had this property of the inverse, okay, function of a function. If you remember from the properties of inverses, that's going to go ahead and just equal the output there. Okay, so what we're going to do is that we're going to take the inverse sine of each side. So we will get this inverse sine of, and now we have the sine of y here, equals the inverse sine of just x. Okay, and just like these two kind of, I don't want to say cancel out, but in essence they do, just to give it x, these guys are also going to undo each other, and this is just going to give us y equals the inverse sine of x. Now, here's the problem, is that this guy right here, okay, there's something wrong with it, as that is not a function, okay, and that means is that it's going to fail the vertical line test in multiple places. Also note that if we were to reflect it over the y equals x axis, the original, from going from sine to the inverse sine, right, it's going to go ahead and flip-flop over here, and this is going to flip-flop over here, and we end up with that reflection where the x and y values switch. So our biggest problem right now is that that inverse sine function is not I shouldn't say inverse sine function. Inverse sine relation is not a function. And so if we take a look at it like this, okay, we see that, again, this is just the sine function where the x's and y's have been replaced, and you notice that it has very similar relationships to the original sine function, except now it's more vertical. And to show the problem with this thing, say if I were to go ahead and ask this guy right here, and notice that this is going to be the inverse sine function, okay? So if I were to ask, all right, well, what angle is going to go ahead and has the trigonometric ratio of sine of the angle whose sine is 1/2, okay? So that means it's going to kick out an angle. Now the bad part is that as is, it could kick out pi over 6, 5 pi over 6, 13 pi over 6, 17 pi over 6, blah, 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 blah. It goes on forever, right? Because we have the input at 1/2 all the way down, okay, that you can see, and it's going to get multiple answers. And that is not useful because, for one, it's not a function, and two, it could kick out anything. So mathematically, what we've done and kind of agreed on is that we trim up this part right here, okay, and let me make that a different color. We trim up this part right here so it does have that one-to-one relationship, and it does pass the vertical line test like so, okay? So this is the recognized inverse sine function. Okay, notice that it will pass the vertical line test, and then when I ask it what is going to be the an angle whose sine is going to be 1/2, it has a definitive answer of pi over 6 or 30 degrees. Okay, and that's super important. So that basically means is that going back to this, okay, I'm going to go back to the very, very first page and explain to you why these are important, okay, is that for all of these guys, and I'm going to start right here, notice that it's hedged up. So this means is that I can ask the domain right here, I could ask any trigonometric ratio from a -1 to a +1, okay, because that's where sine bounces back in between trigonometric ratio of a -1 to a +1. And, oops, wrong direction, Dennis. And that is going to kick out any of the angles that are going to be in the 4th quadrant or the 1st quadrant, okay, because this is where the sine ratios are going to be negative and these are going to be positive. So we have to go ahead and pick from those quadrants the particular degree measure, be it degree or radians, okay? So for example, if I were to say something of this sort to model that, the sine, inverse sine of a -√2 over 2, okay? So in that case, I would have to take a look at this and say, all right, well, this is going to, it has to be in between a -90 degrees and a +90 degrees. So either it's going to go in this direction for positive ratios or this direction for negative ratios. So I know it's negative and it's going to be in the 4th quadrant here, but it's going to go in a negative pi over 4 direction, and that is going to kick out negative pi over 4 or this business of a -45 degrees. So, and the reason why we do that is because, again, it could, if we use the whole unit circle and we don't restrict anything, it could kick out an infinite amount of angles and therefore be useless. Okay, now cosine does the same thing, is that we can go ahead and pick any ratio from the a -1 to a +1, because that is the range of the regular cosine function, and it's going to kick out an angle that is going to be from 0 to 180 degrees or 0 to pi, simply because this is positive and this is going to go ahead and be negative. All right, and we couldn't go in the negative direction because that would be positive as well. So if we went in the negative direction here, that would be positive, and therefore we would have two positives, and that wouldn't make sense. So for example, how to use this: the cosine, the inverse cosine of, let's go, a ratio of a -1/2. Okay, so that means is that I say to myself, what angle, okay, in the first or second quadrant is going to go ahead and kick, is when I take the cosine of it, is going to give me a -1/2. And so I know that the cosine, right, is when I take the cosine of, trying to change some colors here, this pi over 3 is going to give me 1/2 positive. Okay, so I look over here and I think that that is going to give me what? That is going to be 2/3 pi. So it looks like the cosine, if I have 2/3 pi, is going to give, when I put the -1/2 into the inverse of cosine, it is going to give out that, or 120 degrees. Just like the cosine of 60 degrees would give me 1/2, the cosine of 120 degrees would give me a -1/2. So we're just switching those around. And then finally, we have the tangent, and we know that the tangent goes on forever in this type of fashion. So when we reflect it over the y equals x-axis, or we do the inverse, we're going to go ahead and get this part right here. So we're only taking one increment of the asymptotes that are kind of like butterflied around the y-axis and then turn to the x-axis for the inverse, okay? And it has the same choices for the angles, okay? So, for example, if I were to say this business of what is going to be the inverse tangent of, and let's just make this easy, a -1. So I know that tangent is going to be 1 either here or here, but this is going to be a positive 45 degrees, or pi over 4 for the positive 1, and this is going to be a negative pi over 4 for the -1. So I pick from the fourth quadrant, and that is going to be a negative pi over 4 or a negative 45 degrees. Okay. So that's how you do that guy. And in the next video, we're going to take a little bit more in-depth look at these and using this chart below. And yeah, I'll see you in the next video.